Right, we've talked about um, some acid calculations for strong acids and strong bases, where we've been using pH as minus log 10 H plus, but we now need to extend that a little bit and start looking at weak acids and bases, and hopefully bring in some ideas relating to equilibria at the same time. This is what we need to cover. And if we take a weak acid, something like ethanoic acid, very common example, then that only undergoes partial dissociation in water, right? So you can see here it's in equilibrium with these products. And you could also, if you wanted to, you can exclude the water and just list it as that. But we can write an equilibrium expression for that. Okay, so I've taken that, I've written an equilibrium expression for that, and I've got this, because it's an acid, an equilibrium constant, Ka. Similarly for the base, if I take my base, put that in water, I'm going to end up with this reaction. So this is accepting a proton from the water, and again I can write a Kb, right, a Kb expression. Now I'm assuming in both of those that the water is kind of massively in excess and essentially constant, so I'm defining these new equilibrium constants Ka and Kb and leaving out the H2O. But just as we saw with pH being minus log 10 H plus, I can now write pKa, which is minus log 10 Ka, so the P is referring to that function. So stronger acids will have equilibria that lie further to the right hand side and will therefore have larger values of Ka. So if we had a stronger acid, you can imagine it's giving up more of its protons, it's going to be further across to that side, its term's bigger, Ka is bigger. That corresponds to a smaller pKa because of the way that the minus log system's working for us. Right, so there's a link between Ka and Kb, and if I take my weak acid and then think about its conjugate base, I can derive expressions for Ka for the weak acid, as you just saw on the last page, and an expression for its conjugate base, because its conjugate base is going to be doing this when I put in the water, which means its expression there is that. Now the Ka expression will have been H plus A minus over HA, like that. And when I multiply these together, a lot of stuff cancels out, and I end up with this, which is also equal to Kw, the ionic product of water. So we've got this relationship between some quite important terms, Ka, Kb, and Kw. Now experimentally, I can find out the pK of a weak acid by doing a titration. So if I take my weak acid and I titrate it with sodium hydroxide, it turns out, and we'll see later on in this section why, but it turns out I get a curve that looks like this as my pH changes as I steadily add in my base. So at the point of neutralization, all of that has reacted away with all of that, right? That's what the neutralization point is, and I'm left just with the salt and the water, and then I keep adding in my base, and you can see I keep going up like that. However, if we think of our ethanoic acid, CH3CO2H, and I think of its Ka expression, then that's going to be CH3CO2 minus times H plus over CH3CO2H, like that. Now there comes a time, if I'm adding this in, so this product here is the same as that, this over here is the same as that. So if I keep adding this in, at the start I've got lots and lots of this, not very much of that. If I keep adding this in, there'll come a point at which these two, this and this, in other words this and this, have the same concentration. and that's referred to as my half neutralization point. Half neutralization. So if neutralization was at 50, let's say, half neutralization is at 25, and at half neutralization, that and that are the same. In other words, my Ka is equal to the H plus ion concentration, which means my pKa is equal to the pH, and from that I can work out my pKa for that particular acid. Right, so these are calculations which I think you've already seen. If you looked at topic 8, you can see how if we start maybe with this one over here, pH, you're dealing with a strong acid, right? So you've got a strong acid, total dissociation, so every mole of that is going to give you an H plus, so you've got the H plus ion concentration, you just put it into your pH equation and solve it. Strong base, similar idea, we just have to be careful that we're dealing with OH minus ions, so we can talk about POHs, or we can use our KW to help us go across to H pluses, and we can work out what we need to work out. Now, another example here, the pH of water actually changes with temperature. So this process here, and we've seen in terms of KW, if we're at 298 Kelvin, 25 degrees Celsius, then this is KW 1 times 10 to the minus 14, right? Tiny. It's a very, very small number of these water molecules ionize to give us H pluses and OH minuses. Nevertheless, they do. And this is an endothermic process. So that would imply that as I heat things up, I should see it shift to the right. So a warmer temperature like this will give us a greater concentration of products. And the odd thing here, well, I guess it's not odd, it kind of makes sense, is that if I have more of these, I'm going to be seeing the pH changing. And you can see here my pH has indeed gone down. It appears to be more acidic. The solution is still neutral though, because I've got equal numbers of H pluses and OH minuses. The thing is that pH just measures the concentration of H pluses. So if they have increased as they have here, my pH will become lower. However, the water is still going to be neutral, right? Cups of tea don't suddenly become corrosive. So weak acid calculations, this ties in a little bit to our work on equilibrium, because we're going to rely on an important approximation. So I've written my Ka expression, and one of the things I've recognized is that when I take my weak acid, every time that ionizes, I get one of those and one of those. So in other words, these must be the same, which means my top is H plus squared. But I can assume that, because it's a weak acid, very little of this actually dissociates. So the concentration of the equilibrium amount of this will be the same as it was at the start. So that's a key assumption that I have to state when I do these calculations. And then I can work it through. I'm going to get the H plus ions, and then I'm going to get the pH on the back of that. Similar for weak bases, starting from a Kb relationship. And again, you're saying that those two things are going to be the same, so it's squared. Then you're going to make that approximation that because it's a weak base, very little of it actually ionizes. And then you can go through and use Kw to help you solve what you need to do. Now, on this slide, you will see 8 questions, and I would strongly recommend you pausing this and having a go at those 8 on a scrap of paper, and then you can move on, and after that, you'll get the solutions. Okay, so have a go at these, and then the worked solutions are just underneath.